All right, question number 4. All right, so we have to take a derivative here, right? So we have a product of functions x and e to the negative x squared. So we have a product rule, right? We know product rule has 4 parts connected with addition. We know the first and the third are just the functions that we see. And then we get the derivatives of the other things, right? So e to the negative x squared, that's a chain rule, negative 2x e to the negative x squared, and then x over here. Right, so here's f prime. We can definitely pull some stuff out of this. There is an x that can be pulled out of everything. There's also a e to the negative x squared that can be pulled out of everything. So if I pull out x e to the negative x squared, I'm left with negative 2x plus 1. All right, so when is this thing equal to 0? Well, it's going to be equal to, oh, so my bad. Let me check the domain. The domain is all real numbers, right? So x can be any real number, e to the negative x squared can be any real number, so the domain of this function is all real numbers. So our critical values occur when x is equal to 0, when e to the negative x squared would be equal to 0, but that never happens. It's an exponential. This is never 0. And then when negative 2x plus 1 is equal to 0. So that's going to be x is equal to 1. All right, so right now, our kind of domain would look like 0, 1, half. And we can see what f prime of x does there. All right, so let's see. So we know that e to the negative x squared is always going to be a positive number. So this means that our function is now looking like x times negative 2x plus 1, right? This is a quadratic that opens downwards because of this negative 2x. I just don't feel like plugging in like numbers, like plugging in like negative 1 or something, right? So we know that this is going to have two x-intercept 0 and 1/2. So we're negative, we're positive, we're negative. So we're decreasing, increasing, and then decreasing for f of x. Right, so that means that we're going to have a min and we're going to have a max at 1/2. So next thing we need to do is take a second derivative. Right, so what's the easiest form so I don't know. I was going to take the derivative over here. I have a feeling I'm going to need some more space. All right, so if I want to take the derivative of this, was that a negative? I don't know, it's an equal sign. So f prime of x equals this. Okay, we have two functions that we actually are multiplying together. I'm going to be a little sneaky here. I'm going to treat this as one function, two functions for our product rule. And the reason I'm going to do this is because, again, we know that e to the negative x squared is the first term, negative 2x plus 1 is the second, derivative of negative 2x plus 1 is negative 2, and this term would be the derivative of x e to the negative x squared. But good news, that's what we started off with, right? So we already know what the derivative of x e to the negative x squared is. It's this thing. It's this x e to the negative x minus 2x plus 1, or this thing that was in green. So I could just take this entire green thing and duplicate it, and that's going to be our derivative. That's what this derivative is going to equal. All right, so I'm going to rewrite that a little bit. So we would get the second derivative is equal to negative 2x e to the negative x squared plus negative 2x plus 1 times another negative 2x plus 1. So that's going to be squared. We have an x e to the negative x squared. Again, we can see that we have some common factors. I have an x e to the negative x squared that appears twice. So we would pull out x e to the negative x squared. We'd be left with negative 2 plus negative 2x plus 1 whole thing squared. All right, so then where does this thing equal 0? By the same logic, when x is equal to 0, e to the negative x squared is always positive. If I solve this for 0, I would get negative 2 plus 2x plus 1 squared is 0. I can bring the 2 over to the other side. So negative 2x plus 1 squared is equal to 2. I can root both sides. And because this is not my first time taking a square root, I'm going to obviously remember that we get a plus or minus. Negative 2x plus 1 equals that. So I can subtract the 1, divide by negative 2. So x is equal to negative plus or minus rad 2 minus 1 all over 2. And I could rewrite that a little bit more. I could say if I distribute this negative in, I would get x equals minus or plus radical 2 plus 1, which I'm just going to rewrite this way. Like that. 1 minus or plus radical 2, which is going to be the same thing as plus or minus. It doesn't matter. It's a conjugate, and then divided by 2. Okay, so those are our values, and now lot going on. I probably should have given ourselves a different page here. So we have potential concavity changes at 0. 1 plus radical 2, right? Radical 2 is about 1.4. So that's going to be like 2.4 over 2. That's going to be like 1.2-ish. So here's our 1 plus rad 2 over 2. And here's 1 minus rad 2 over 2. So that's like negative 0.4 over 2. So this is going to be like negative 0.2, something like that-ish. All right, and then just because I don't really feel like plugging in values a whole bunch of times, I'm going to graph this thing. So if I were to look at what the graph of xe raised to the x, whoops, negative x squared. What do I even have? Xe to negative x squared. Then we are multiplying this by negative 2 plus, in parentheses, negative 2x plus 1 squared, close my other parentheses, make this thing y equals, so graphs, zoom in a little bit. All right, so here's our function. Right, we have zeros there, and there, like we found. I'm not going to pat myself on the back for my quick mental math. So we know that this function is negative to the left of negative 0.207, positive between negative 0.207 and 0, negative, and then positive. So we're getting negative, positive, negative, positive. So negative, positive for a second derivative. So concave down, concave up, concave down, concave up. Right, so this would be an inflection point. This would be an inflection point. This would be an inflection point. And this one is done.